So hello everyone, this is lecture 6 for the atomic physics. In the last lecture we have completed the Bohr's model and all the related questions. So today we will discuss Sommerfeld's model and why we are discussing this. Because normally we know that there is this one line we observe, H alpha line, L alpha line, we observe these lines. But see, this was the case in the ancient times, but when there was development in the spectroscopy and we have more resolved spectroscopes. So what we get is there are multiple lines, means in the single line we can observe two lines or three lines, or they are superposition of multiple lines. So why we are getting different lines in the single line? So that's why this model was introduced, means he introduced some theories and gave. So that's how he can explain. He tried to explain. Okay, so he was able to explain somehow, but that was not the true condition, means not the complete condition. We will discuss that how this thing is developed and how we discuss the Paschen-Beck effect, and we will discuss the Zeeman effect and all, so hyperfine structure and all. So we will lead to there. So it is first the Bohr's model, then the Sommerfeld's model, then spin orbit coupling and all. That's how we will develop this. So what was Sommerfeld's model? He used the Kepler's law, means inside an orbit. So in the Bohr's model, we see that there is only circular orbit, but Sommerfeld said that no, there will be some elliptical orbits also, and that lead to these multiple lines. So how it will? So let's see what is the theory. The picture presented by the Bohr was not perfect. The lines of Balmer series consist of several components as seen in the figure. So this was the actual figure. When you have more resolved, now the lines of Balmer series consist of several components as seen in the figure. In the spectrum of one electron ion, helium plus, these multiplet lines are more strongly separated, and the splitting is easier to observe. So if we observe for the helium ion, then they are more strongly separated, means you can clearly see these lines. These are multiple lines. So why these are? To explain these observations, Sommerfeld extended the Bohr model. His model was based on Kepler's law, which says that apart from the circular orbits, various elliptical orbits, orbits having same energy are possible in case of the Earth, astronomical body, revolving around the Sun. As I told you, this is the same thing. Sommerfeld applies the same concept in atoms. He introduced a new second quantum number, that is k. Later it was become the orbital quantum number, that is L. So we'll see that how we develop this. So he introduced the second quantum number, that is k, to represent the elliptical orbit along with circular orbits with same energies. He was saying that principal quantum number n determines the total energy of an electron in an orbit. So we know this formula already from the Bohr's model, that energy in particular quantum number n is defined as En equal to minus RSC by n square z square. So he said that energy will remain same in the orbit whether it is elliptical or circular, but there will be orbit change with k, means different k will be possible for one n. So with this energy, many orbits are possible. They may be circular or elliptical because the energy of circular and elliptical orbits are same. So the length of the major axis will be same for all the orbits having same energy. For in the central forces, we studied in the classical physics that energy of an elliptical orbit is given by equal to minus k by 2a. So this a is nothing but major axis. So for same energy, this formula will remain same, and this major axis will remain same. So for all the orbits, this major axis will remain same. That is the conclusion here. Under the inverse squared force law, we studied this thing. So what will be the case? There will be circular orbits for different n, and there will be elliptical orbits. And how it will be defined means like there is n. So the k will be 1 to n. If n is 1, then k will be 1. If n is equal to 2, then k will be 1 2. N equal to 3, it will be k equal to 1 2 3. So that's how k will be defined for particular n. So they will have the same major axis and they will have the same energy. Okay, for particular n will define what will the energy, and k will define that what will be the orbit. So Sommerfeld gave the following formula for the length of the semi-major axis. So this was the formula. This is the same as we used in the Bohr's radius. So equal to a naught n square by z, because the semi-major axis will remain same. That's why this can be defined as this. Now in the why it is means why we are getting the elliptical orbit. So we know in the central force system, this is the energy given by that. So half mr dot square plus L square by 2mr square plus Vr. Now see, if angular momentum is changing but total energy is remaining same, then you'll see that different orbits are possible. So that's how he explained this, that energy will remain same and L will change. So that's how k will become L. To represent various types of orbits having same energy, introduce second quantum number k. He was saying these orbits of same energy have different angular momentum, which will remain integral multiple of h cut. Now in the Bohr model we studied that angular momentum is defined as n h by 2 pi. Now he replaced this n by the k, so L is nothing but k h cut. So k is Now k will be like, means angular momentum will be like k h cut, so it will be 1 h cut, 2 h cut, 3 h cut, like that. So in place of L you will just substitute these values and you will get different orbits. So now this equation, if angular momentum is different and energy is same, then surely different shapes of elliptical orbits are possible, as observed by the formula of total energy in the central force problem, that is this. Now in place of this VR potential energy, we can write minus k by r, as the in the central force system we know this. K is nothing but gmm, that and r is the distance, radial distance. So that's how we can just define this total energy now. So see what we conclude here. The shape of the orbit is governed by the length of the semi-minor axis. Now see, the energy is defined by the semi-major axis, that is by this a n equal to a naught n square by z, that will remain same for all the orbits. But shape of the orbit is defined by the semi-minor axis, that is b, and it will be depending on n and k both. So it will be a naught n k by z. If n is 1, then k will be 1, so it will be a naught by z, and n equal to 1, then a will be a naught by z. So see, a and b both will be same for n equal to 1. So that's why for n equal to 1 we have circular orbit like the Bose orbit. But for n equal to 2 you will have 1, 2 and 2, 2, means 2 combination will be there. And for n equal to 2 and k equal to 2 you will get the same thing, a and b. So again you will get circular orbit and one elliptical orbit. So that's how for the greater n you will get multiple orbits. So this will governing shape b, and this major axis will governing the energy. So you must remember this. For n equal to 1, k equal to 1, b equal to a naught, a equal to a naught. So you will have circular orbit for n equal to 1. For n equal to 2 you will have k equal to 2, k equal to 1, and similarly for k equal to 2 b will be 4 a naught, as 2 to a 4 a naught for z equal to 1, and a will be 4 a naught. So for k equal to 2 you will again get circular orbit, that is Bohr's orbit. But for k equal to 1 you will get 2 a naught, b is equal to 2 a naught, and a equal to 4 a naught. So you will get this orbit. And now this is what introduced by the Sommerfeld, means normally you are having this thing in the Bohr's model, but now you have this also. For n equal to 3, again for k equal to 3 b and a will be same, but for k equal to 2, k equal to 1 you will get different elliptical orbits. So that's how for higher n you will get more and more elliptical orbits. So that is what given by the Sommerfeld. Later on in quantum mechanics, this k number become orbital angular momentum, as I told you, L, and L is nothing but k minus 1. So as n is principal quantum number and k will go 1 to n, so L will be k minus 1, that will be 1 minus 1, 2 minus 1, 3 minus 1, 4 minus 1, that will be 0, 1, 2, 3, and that's how you define the SPDF orbitals. So this is this, L equal to 0, 1, 2, 3, and minus 1 up to n minus 1. So SPDF, these different values of orbital quantum numbers are corresponding to SPDF orbits. So that's how you get the different orbits as we see in the quantum mechanics. So lifting of orbital, now see that what is happening here, means we defined this model to get different lines, but to get different lines we must have different energy. But here we are saying that all time we are saying that energy will remain same, energy will remain same. Then how we are getting these different lines? So see, to lift this orbital degeneracy, so we will use the relativistic mass change. So what is relativistic mass change? So in the Kepler's law we know there is area law of areas. That means in equal interval of time, the area covered by this object will be remain same, means planet will remain same, whether it is here or here, the same area will take the same time. So see, this distance is small as compared to this, so here to cover the same area speed must be increased. So as speed increase, so just like in the normal solar system, we are assuming this case in the atom. So we will see that for the nucleus, this speed will be very large, means up to the relativistic stage. That's why there will be mass change inside the nucleus or inside the atom. So what will happen when mass will change? So mass change will give you the energy change exactly. So lifting of orbital density by relativistic mass change. To explain the presence of many lines in the H alpha, H beta, etc. Balmer lines, he introduced a relativistic mass change for moving electron. Now moving electron will move fast here, so its mass will change. So from the Bohr's model we know the energy formula, minus 2 pi square m naught E4 z square, 4 pi epsilon naught square n square h square. Now see, this is the rest mass. Now again for the relativistic case, this will be given by m, that is m naught by under root 1 minus v square by c square. This mass will increase. So when mass will increase, this whole term will increase and it is in minus, so energy will decrease. So E dash energy will be less than E, means here energy will reduce as compared to here. So you will get different levels. In first you will have this level, now for this area you will have a lower level. Now see, for higher smaller k, for k equal to 1, k equal to 2, you see as k is decreasing, this b is also decreasing. So for smaller b, you will get more area covered here or more circumference covered here for the higher speed. So there will be a large effect will be seen here for the lower energy or relativistic phase. So Now see, m will be greater than m naught and e dash will be less than e. So how they are giving us different lines. Now see here, first you have this case for the means n equal to 1, n equal to 2. For n equal to 2 you will have k equal to 1 and 2. So you will have two levels. And how you are getting these two levels? See, first level is here. When your electron is here, there is no relativistic case, so it is same energy is there, but as it reaches here, energy will decrease, so you will get this second level here. So for same E2 you will get this second level here for the particular reason, the relativistic case. And this is E2 dash, this E2 energy, and this is E2 dash, and E2 dash is less than, as I already shown you. So n equal to and k equal to 1, this is the case. If now see, when electron is close to nuclei, this is the level. Now one line you will get from for this, and second line you will get for this. So that's how you will get two lines. Now that's how Sommerfeld explained these multiple lines. Now again for Balmer series also you can see that for H alpha line there will be n equal to 2 to means 3 to 2 transition, and that transition means for n equal to 3 you will get k equal to 1 and 2, and again you will get multiple lines. So there will be more lines will be there. So that's how Sommerfeld explained this. So this somehow made the base of these all developments, that how we are getting multiple lines. Now we will more refine this means we will refine this more, and we will see that how we are getting more and more lines, multiple lines in the hybrid structure and all. So that's all for today. Here we end the Sommerfeld model. So thank you.